Hi, welcome to my Lab 3 video report. In this lab, the experimenter focuses attention on the magnetic field of permanent dipole magnets. In this lab, the experimenter was tasked to investigate the distance dependence of a small bar magnet and to compare the distance found during the experiment to that predicted by the appropriate formula from the Biot-Savart law. The experimenter has the following objectives. Using a bar magnet and magnetometer, take and record the distances at which specific absolute values of the magnetic field were taken. Using key physics concepts, calculate the experimental magnetic dipole moment, mu. Using the calculated value for mu, as well as the coding on GlowScript, calculate and depict the magnetic field of the bar magnet at different locations, and compare the expected results from the code to the experimental results found. The following materials were used in this experiment: a bar magnet, a magnetometer app on the phone, 2 rulers, tape, and a provided Excel sheet. Before starting the experimenter needed to compensate for the net magnetic field of the Earth based on the location of the said experimenter. According to the suggested website, the magnetic field at the location of the experimenter was 38.26 microtesla. Therefore, by using experimental data from the phone, magnetic fields seen in the picture to the bottom left were used. To locate the magnetometer chip, first the experimenter aligned the ruler orthogonal to the base of the phone while aligning north to compensate for the magnetic field. By doing this, the ruler is placed along the east-west axis. A magnet was placed at one end of the ruler. The phone was moved perpendicularly along the ruler until the absolute value of x was at its maximum. A piece of tape was placed on the phone at this place, where the edge of the tape was in line with the upper edge of the ruler. The phone was rotated 90 degrees and the same procedure was repeated. The upper corner of the phone marked the location of the chip. Using this setup, the experimenter was tasked to find the distances at which certain magnetic fields were located. For example, from the data seen on the left, the distance at which a magnetic field of 20 microtesla was observed was at 11.7 centimeters away from the magnet. Using the accumulated data, a baseline graph was made. And by using a similar approach, the experimenter was tasked to find dipole, where a magnetic field of 100 microtesla was observed 45 degrees away from the magnet. The following key concepts were used in the experiment: the Biot-Savart law, the magnetic field of a dipole on its axis, where r is much greater than the separation distance, and the typical equation for the magnetic field of a dipole. Now, using the given formula and the graph found earlier, the experimenter is able to calculate the value for k by taking e to the power of the y-intercept. Therefore, k is equal to e to the negative 17.422. And to find n is much simpler, as n is the slope of the line. Hence, n is equal to negative 3.0845. Now, by comparing k to the dipole on the axis equation, we can see that k is equal to mu naught over 4 pi times 2 times mu. Therefore, mu is equal to e to negative 17.422 divided by 2 times 1 times 10 to negative 7 to give you a value of 0.1357. The first steps in creating the code were to input physical constants, create a bar magnet as a cylinder, enter the value found for mu, and then create a function to calculate the magnetic field. Afterwards, using the axis created and magnetic field functions, arrows were generated to depict the fields on axis and perpendicularly to the magnet. Then finally, to create arrows 90 degrees from the magnet, dperp and the magnetic field function were implemented, resulting in a pictorial representation seen here. To conclude, the experimenter needed to compare the experimental and expected results. For the expected results, we expected n to be negative 3 from the Biot-Savart law, and that the magnetic field at 45 degrees should have been 4.3 times 10 to the negative 6 Tesla, 1.291 times 10 to the negative 5 Tesla in the x and y components, and that B net should be 1.36 times 10 to the negative 5 Tesla. However, the experimental value gave us different results, in which n is negative 3.0845, and that B net is 105 microtesla. So what does this mean? The percentage error between the experimental and expected results for the magnetic field are too high when calculated. Despite efforts to take precautions during the experimenter did have difficulties maintaining a stable hand. Some of these precautions included conducting the experiments by a workplace away from electronics, as well as aligning the phone with north properly before starting. One thing the experimenter had noticed, however, is that the Z component is included in the experiment, whereas no Z component is used in the code. Assuming that the experiment was conducted to account for the Z component of the magnetic field of the Earth, perhaps the experimental data would better match that of the expected data. All in all, thank you for listening.